plus c. And we know that this is going to work if I take the derivative of it, because this 1/5 and this 5 that we were missing before, or this extra 5 that we actually picked up, are going to cancel out, and I'm going to get 5x to the 10th. Isn't that awesome? Let's do one more, and I'll let you guys go for this little portion. This part, I'm going to let you go, and then we'll get more complicated down the road. All right, how about this one? How about, let's see, the sine of, let's just go 2x dx. The antiderivative, you know what? I'm going to keep things clean with negatives. Let's call this the cosine instead of the sine. So I'm going to say the cos of 2x dx. All right? Again, really what you're asking yourself, and this is the thing, the hard thing about integration by substitution is sometimes you'll make a substitution and it just doesn't work. In other words, how can you tell that it doesn't work? The integral doesn't get easier. You always have to ask yourself, am I making an integral easier? Because if I'm not, stop what you're doing. You're going to make your life harder than it needs to be. Excuse me. So think about it. What would make my life easier? Well, if this were gone, if this were just cos x dx, life would be easy. The antiderivative of cos x is sine x plus c, and life is good. So we substitute that out. And that tells us also, hey, I composed 2x into cos, and now we're just dealing with it. Now, I'm going to do a little trick here. I'm going to get increasingly, not lazy, but I'm going to cut some steps. Remember over here, and in the earlier problem, I did the du over dx. Now I'm just going to cheat. I'm just going to go du equals 2 dx, because I know that I would algebraically send the dx across anyway. Again, the question is, do you see a 2 dx anywhere in this? No, you only see a dx. So I end up with du halves equals dx. Sweet. The dx is accounted for. The nasty bit that is completely accounted for. So I know that this integral equals, notice my 1/2. Now in one fell swoop, I'm going to pull my constant out in front. I'm going to turn this into a cos u du. And look at how easy that got. This turns into 1/2 sine u plus c. Remember, this was a function of x, this is a function of u, but I have a bridge. Think of it as a bridge, right? This substitution bridge, it can always get me back and forth from u to x. And this turns into 1/2 the sine of 2x plus c. If I don't believe myself, take a derivative. Just take a derivative in your head. The sine of blah, well, it's going to be the cosine of blah, that's cos of 2x. I'm just going to use an implies here. I'm going to get a cosine of 2x times 2, because chain rule spits out a 2, and look at this happy little 1/2 is sitting right here. Cosine of c is 0, right, plus 0. These cancel, and I end up with the cosine of 2x. Isn't that magnificent? And I'm good to go. All right? Let me do one more for you, just for giggles. Just one that initially will make you limp and tremble, and then you will just giggle at how easy it is. How about this? The natural log of x over x dx. Right? You look at it and you're like, I see. Well, if I don't have a product rule, there's no freaking way I'm going to have a quotient rule. It's not going to happen. So I look at this and I'm like, well, there's not an easy little composition. Nothing's really being composed into the natural log, and I don't even know how to deal with this 1 over x thing. So I go to kind of that initial question, that simple initial question, because what's going to happen is you'll start being able to do these antiderivatives in your head. Down the road, these will just pop out of you. I mean, it just becomes rote. You don't have to think about it. Do you see a part of this integrand that is a derivative of another part? Well, hopefully you see this easily. Well, isn't 1 over x the derivative of the natural log of x? Of course. So watch what happens. If I let u equal the natural log of x, I know that du is equal to 1 over x dx. And hallelujah, that is exactly, don't you agree that this could be written as dx over x? It's exactly the same thing. So really, this integral turns into, ln x is u, I accounted for this, so this is the integral of u times what? Well, dx over x, which is du. Look at that. That's one of the simplest antiderivatives to take. This is u squared halves plus c. And I'm just going to back substitute to get back as a function of x. This is the natural log of x. Be careful here. It's not the natural log of x squared. It's the natural log of x squared over 2 plus c. And if I wanted to prove it, I could take the derivative of this, and I would get the integrand, and life would be glorious. All right, in the next little segment, I'm going to save this segment. I'm going to give it a little break. We'll move on to the next little segment. We're going to start dealing with, I'm going to do a bunch of examples with you, just have some fun, and then we're going to deal with definite integrals around integration by substitution, okay? And that's going to be it, man. That's it for the semester. You guys have come a long way. So enjoy. I'll see you in the next segment. And hey, everybody, it's Ripley. I'm back again. I want to do some more integration by substitution with you guys, but we're going to do some definite integrals, okay? So now we're going to throw in some definite integrals. Now, the cool thing about definite integrals is, believe it or not, they're almost easier than the indefinite integrals, the ones that don't have any limits on them, okay? So I'm just going to do a couple of examples for you. I'm going to do this integral, and we're going to call this, let's do the integral from 1 to 4 of e to the root x over root x dx. Now, same rules apply. Look at it. It's not a simple, you know, let u equal 2x or let u equal, you know, something, I don't know, 5x or something like that, like we had back with like sine of 2x. This one's a little trickier. This is the one where you want to look at it and say, are there any parts of the integrand? Oh, wait, back up. First things first. Is this an integral that we've memorized? Do I know this function? You know what I mean? That's the first question that you want to ask yourself is, have I memorized this one? Is this one of the Fantastic 15? Is this one of my good friends that's on the hard drive? That's the first box that you want to check in your checklist, because if you memorize the thing, just take the integral. The hard part about doing these kinds of integrals is that you're going to get a bunch of skills, and you're not going to know when to use the skills. All right? Substitution is going to do the heavy lifting for most of the integrals that you're going to do. However, that doesn't mean that it's going to happen all the time. And that gets really frustrating, both for me and for my students. But that's okay. You'll get in the habit after you've seen a blue gazillion of them. Okay, so here's what I'm looking at. I'm looking at, let's see, 1 over root x, 1 over root x, 1 over root x. Let's see. If that were a 1 over 2 root x, I know that this is equal to the derivative of root x, right? Hey, wait a sec. That root x, that might come in handy. So let's just go down a path. Let's see what happens. If I let u equal root x. Now, the thing that I really have to pay attention to here is, which root x am I going to let the u be? Am I going to let it be this guy, or am I going to let it be this guy? All right, and I'm actually going to do it where I let it be this guy, and we'll watch what happens later, but I want to do it correctly first. Okay, so here we go. You ready? I'm going to let this u be this root x. Okay, well, I know that du is equal to 1 over 2 root x dx. I don't want 1 over 2 root x. I want 1 over root x. So that implies that 2 du is equal to dx over root x, which is exactly what I want. Now the question is what do I do with these limits? I got these limits right here, okay? Now if you think about it for a second, these limits are on x, right? I'm saying, right, these are the limits that would be on this function from 1 to 4 of x, but u is a bridge to x. So there's absolutely no reason that I can't redefine my limits in terms of u. And it's really easy to do. I'm going to go u of 1. Well, what's u of 1? If we think of this as u of x, then u of 1 is just root 1, right? Which is affectionately known as 1. And then u of 4, which is root 4, which is 2. Now here's the coolest part. Do you remember back when we were doing integration by substitution, and we didn't have to, and we had to back substitute. Let me back it up. Remember all these guys? Okay, so like right here to here, we had to back substitute our u, which was right here. From here to here, look at this, boom, and then we had to back substitute our u. Same thing here, right here, and then we back substituted our u. Well, over here, once I have done this move, once I have changed limits, no need to back substitute. That's the best part about just, all I got to do is redefine my limits in terms of u rather than an x, and I'm off to the races. Okay, so let's fill everything in. I know that dx over root x, which is this term right here, is actually 2u. So when I rewrite this integral, I know that instead of being the integral from 1 to 4, it's going to be the integral from 1 to 2. All right, I know that dx over root x is 2 du, and I know that e to the root x is e to the u. Again, that gets tricky because you've got root x's all over the place. So I'm simply going to rewrite this as e to the u times 2 du, because 2 du was dx over root x, right? Now that's a constant, so I'm going to suck it out here, and I get 2 times the integral from 1 to 2 of e to the u du. Look at that. That's the easiest integral in the world. From what was ostensibly the ugliest one in the world, look at what I have here. So this becomes 2 times 2 times e to the u, the antiderivative of e to the u, is e to the u, just like the derivative of e to the u is e to the u. And I'm going from 1 to 2. And guess what my answer is? It's 2 times e squared minus e. Ta-da! And I'm done. Now, watch what happens if I get confused here. Let's say that I think that this is actually this guy. Now watch, I'm going to try to account for everything, okay? Here we go. So I'm going to let u equal root x, and I'm going to let du equal 1 over 2 root x dx. Now, what happens here? I suppose that I could solve for dx if I wanted to. But the problem is what am I going to do? I'm going to have a 1 over u to account for this, right? And I'm going to have an e to, oh, what's going to happen here?